Intermediate Algebra, Section 7.3, Multiplying and Simplifying Radicals. We've used the product rule for radicals to find products and also to simplify radical expressions. For some radical expressions, it's possible to do both. First find a product and then simplify. In this first example, they're asking us to take the square root of 18 times the square root of 50. They both have the same index. So we'll combine them underneath the radical. But instead of multiplying them into a larger number, I'm going to break it down. 18 is 2 times 9. 50 is 2 times 25. And I have method in my madness for breaking them down this way. 9 is a perfect square. 25 is a perfect square. And I have a pair of 2's. So I can now take the square root of 9, the square root of 25, and the square root of that pair of 2's, which is a perfect square. Square root of 9 is 3, square root of 25 is 5, and the square root of 4, or having a pair of 2's, brings out a 2 when we simplify the radical. Now it's just a matter of multiplying those numbers together. 3 times 5 is 15 times 2 gives us an answer of 30 for our final answer to this problem. In the next example, we're asked to take the fifth root of 16 times the fifth root of 18. Since the indexes are the same, we will combine them underneath the same radical. 16 in prime factorization is 4 2's multiplied together. It is 2 times 2, which is 4, times 2, which is 8, times 2 is 16, times 8, which is 2 times 2 times 2. We're looking for a group of 5 of one thing, and we do have a perfect power here, or fifth root. 2 to the fifth power is represented here, and the fifth root of 2 to the fifth power is a 2, and leaves a remaining 2 times 2, which we could multiply back together as 4. The other way we could have done this is a prime factorization. 16 is 2 to the fourth power. 8 is 2 to the third power. We have common bases at our exponents, which would give us 2 to the seventh power. And if we simplify, putting this in rational exponential form, the fifth root is the same as taking 2 to the seventh and raising it to the 1/5 power, which gives us 2 to the 7/5. 5 goes into 7 once, and there's our 2 to the first power, and leaves a remaining power of 2 left over. 2 to the second power is the 4. And this lends itself to do this mentally, if we're up to it. In the next one, they're asking us to multiply these radicals together, and to ensure that they are in simplified radical form, all factors in the radicand can be written with exponents, or must be written with exponents less than the index. So instead of multiplying these into a larger value, let's break it down. 12 breaks down into a prime factorization of 2 times 6. 6 is 2 times 3, and we have the x. 4, while I'm at it, is a 2 times 2. We have an x from the first radical and an x from the second radical. We're working with a square root here, so we're looking for pairs. We have a pair of 2's. The square root of 4 is 2. The square root of another 4 is another 2. And the square root of x squared is x. And leaves the 3. 3 is to the first power. That makes this a simplified radical. And to clean this up then, do the multiplication. Our final answer would be 4x times the square root of 3. Looking at a couple other examples, here we have the cube root of 5x to the second times the cube root of 50x to the second. Combining those and writing them in prime factorization helps us with the simplification. We have a 5. 50 is a 5 times 10, and 10 is a 5 times 2. Common bases multiplied together, we can add the exponents together. We have a group of 3 5s, and when we take the cube root of 5 to the third power, we get a 5. 2 is only to the first power, it will remain underneath, and if you divide your exponent by the index on the x term, 4 divided by 3 is 1. We have x to the first power with 1 remaining, which means underneath the radical we'll have our 2 and we will have our x. And again, if this is difficult to see, write your prime factorization. And if I just do for the x to the fourth power here, the cube root of x to the fourth, since x to the fourth is 4 x's multiplied together, we're looking for 3 of a kind. That group of 3 comes out in front of the radical and leaves our x to the first power underneath. Each of these quantities is to the first power. It's a lower power than the index, which is the requirement for simplified radical form. In this next one, we actually have 3 things multiplied together. The 3 and the 5 are outside of the radical, so we'll just multiply them as normal, 3 times 5. But multiplying the radicals together, we can combine our radicands. I'm going to leave this 7 prime factorization. 14 in prime factorization is 7 times 2. Common basis multiplied together with the x's. Multiplying the radicals together, we end up with x to the 3 plus 4, or 7th power. Well, 3 times 5 is 15, but we're going to take the square root of 49, or we have a pair of 7s, which brings out 7. We have 2 to the first power. Nothing can be done with that, but x to the 7th power is going to be simplified by taking that power, 7, and dividing it by 2, since the square root is equivalent of raising this to the 1/2 power. So we have 7 halves. And let me write that. We have the 2 underneath here, and I guess I got a little crazy with I want to write this as a rational exponent, so I'll get it yet. The square root of 2 stays underneath, and instead of radical form, I've translated or transformed this x to the 7th to the 7 halves. The index becomes the denominator. Now 7 divided by 2 goes in there 3 times, since 3 times 2 is 6 with 1 left over. That means we would have our 15 times 7. We'll have an x to the 3rd power, and we still have 1 remaining x left underneath there. You also could have written x to the 7th power out in expanded form and pulled off pairs of x's. You would have had 3 pairs of x's that come out, leaving 1 odd one underneath the radical. And to clean this up, 15 times 7, multiplying those integers together, our final form of this would be 105 x to the 3rd power times the square root of 2 to the x. In this last example, we're taking the cube root of these quantities. They happen to be the same binomial. Multiplication of radicals we can combine underneath a single radicand, and since these are common bases multiplied together, we can add our exponents. X plus 2y to the 5th power times x plus 2y to the 4th. Common bases, add the exponents, means we have this to the 9th power. Exponentially, if we translate from radical form to exponential form to help you see this, and again, you may be at the point you can do this mentally, this would be the binomial to the 9th power raised to the 1/3 power. Because of the radical, index becomes the denominator of our exponential power, similar to what I translated up here, an equivalent value. We now have a power raised to a power where we multiply exponents together. 9 times 1/3 is 9/3. 9/3, and let me write that, simplifies into 9 divided by 3, or a 3. So our final answer here is the quantity x plus 2y raised to the 3rd power.